Welcome, Dr. Jangir.
Altaf, good afternoon. How are you?
Yeah, good afternoon. Fine, fine. How about you?
Yeah, good. Thanks. Yes, Altaf.
Altaf sir, we have entered all the details, sir, in the form.
Okay, okay, fine.
Okay.
Actually, I'll try and get the certificates as early as possible for all of you all. But there are some issues which are still pending. Uh, some of the candidates have not filled the transaction form yet. So we need to first verify the transaction and then we'll proceed with the certificates. So kindly, all those who have not done it, please do it at the earliest. We can start in 2 minutes. We'll wait for 2 minutes max.
Thanks, Altab. So today also, I mean, myself and one of my former student, Dr. Sorab Nizami. So both of us, I mean, together will be conducting today's session. So as I mentioned, like so far, we have only given focus on the technology and generation side, but as you know that like for the future market, either we call it smart grid or even for microgrid. So it's not only the generation, I think the market and also the consumer or prosumer participation in the market needs to be changed as well. So Dr. Saurabh, I mean, he worked on transactive energy management, and that's comparatively new topics. And currently there are number of research projects going on in that area. And I hope all of you, I mean, you will enjoy this session because this is more like on the economic and optimization side, not the like in the technical side. So Saurabh, are you here?
Yes, Professor, I am.
So first, I mean, Saurabh will, I mean, present, I mean, some of his research outcome. And then, I mean, depending on the time, I mean, I'll go for the rest of the time. So if you are ready, Saurabh, I mean, please share your screen. And when you are ready, I mean, you can start.
Sure, definitely.
Welcome, Saurabh.
Thank you. Let me just give me a moment to start my screen sharing. Which one is one?
So sort of like every 10-15 minutes, just give them like, some time just to see like whether they have got any question or comment they would like to have.
Definitely. Can you see my slide show screen or?
Yes, I can see. What about Altaf? Can you see slide?
Yes, visible as well as audible.
Thank you.
Good. Thank you, Professor Jangi, and thank you, Altaf, as well, for inviting me here. I'll just give you maybe a quick intro, like a very short one. So my name is Sohrab Nizami. I was a former PhD student of Professor Jangi when he was at Macquarie University. I do have a slide here, I guess. Yeah. I did my PhD in 2020 from Macquarie University. Professor Jahangir was my principal supervisor there. It was basically to look into how we can integrate distributed energy resources more efficiently into our electricity power system, and also what sort of interaction would be more suitable going forward for market bidding and market mechanisms when you have higher share of distributed energy resources. And then I worked for a company called EV Energy, which is in Sydney, Australia, as their e-mobility research lead for about a year. Then I moved here, currently where I'm located in Brisbane, Queensland. I work at the University of Queensland as a research fellow in e-mobility. So my main research focus these days is mainly around how to optimize grid integration of electric vehicles and how to capture more benefits from flexible operation on smart charging of electric vehicles when they integrate into the electricity market. So basically kind of the same pathway that I've been doing in my PhD, but it's more focused on electric vehicle, not just any source of distributed energy resources. So this talk here, I thought I would discuss some of the findings that I had in my PhDs. So the topic that I choose here is called transitive energy management for residential distribution networks with high levels of distributed energy resources. So that means look into how transitive energy management system can be beneficial going forward for especially for residential networks of which have a higher penetration level of different distributed energy resources. So the slides are a bit long, but I don't know how long do I have or how much time I would need. But yeah.
So I mean, the total duration is 2 hours, so you can continue. I mean, as
That's
long as you want, no
That's
problem.
long actually, then the slide is short. All right. Okay, so I do have a few background slides to discuss about the background and evolution of transitive energy and how that evolved, and then going into some overviews and features of transitive energy management, mainly focusing on residential networks. Then I'll discuss about some applications with their specific opportunities and challenges. And then I'm going to present a few case studies from some of my research works from my PhD. And I'll point out some future research direction in this particular domain if any one of you are interested. So the big picture is with the modernization of electric power system, that modernization is mainly driven by 3 Ds that I would like to say is decarbonization, decentralization, and digitalization. So obviously the names are quite self-explanatory, but I just want to take a few minutes of time to explain through how this is affecting the current framework and operation of power system and electricity market. So with the decarbonization, obviously there's a huge drive to reduce the CO2 emissions. With that, the trend that we have been seeing in recent years is like more and more fossil fuels generation plants are retiring. For example, if you look through the uh, all the developed countries, especially the coal was the major source of power generation until a few decades ago, but these days the generation from coals are quite deteriorating, and governments around the world are actually retiring these coal-fired power plants. Same thing is happening here in Australia as well. For example, I have this chart on the right hand side and the second chart on the right hand side. It shows the year by year planning stage in terms of when the Australian government is planning to retire its existing coal-fired plants. So as you can see here, the number gets quite congested after 2030. So they kind of retiring one coal-fired power plant on average in each year on average. The same thing is happening almost in all the developed countries. So we don't have coal. That means we have renewables coming in to fill in the gap. And according to the IEA outlook and IEA statistics, we kind of passed the 1/4 of power generation from renewable electricity. That we passed that mark in 2018 and 2019. So these days the percentage is even higher, maybe on the around in the range of 30 to 35%. So, and out of these renewables, obviously the solar and wind are the more dominant one that we've been seeing, as more and more electricity are being generated from these outlets.
Sorry for the interruption. I think you can use like that digital pointer. I mean, just right click, then probably they can see better.
Really? I haven't used WebEx before. Is it like a pen or a
Pointer just is, can you see like any pointer?
pointer option? Yes, there's kind of a pen. Yeah, can you see my pen now?
Yeah, I mean that's yeah, I think they can see it. Yeah, yeah.
Oh, good. Yeah, that looks good. Thank you. I don't usually use WebEx.
Okay.
All right. So yeah, so we have more and more renewables coming in, and with that decarbonization as a byproduct, we have decentralization, because most of these renewables, especially if you look at the solar PV generations, they are happening in small scale and they are distributed. That means they are connected in the low voltage side and medium voltage side, in most cases behind the energy meters of the consumers. And in some countries, in some regions of the world, the number has been quite extraordinary. For example, if we look at Australia, I think the data here is actually at 2 years old. So we had around more than 10 gigawatt of installed rooftop solar PV systems in Australia from small scale residential applications. And this is the data from 2020. So I believe these days it would be much higher than that. So we have decarbonization and we have decentralization. The next next step in the modernization of the electric power system is digitalization. So we have advanced information and communication system for seamless flow of information both ways in the power grid, and with that emerges the current form of our electricity power grid that we are widely known as the smart grid, and that facilitate and support bidirectional flow of information and also bidirectional flow of power, which is obviously triggered by the introduction of small scale renewable electricity being centralized and connected behind the energy meter. So these 3Ds, this decarbonization and decentralization, means we have more renewable energy sources into our power generation mix. That means that helps us reduce our CO2 emissions, but that comes with its own problem, because this is complicating the supply demand balancing in modern power system. What I mean by supply demand balance is that most of these renewables, if you look at solar and wind, they're highly dependent on weather conditions, and they have limited controllability on in terms of how much they can generate at a particular time of the day. And sometimes it can be quite unpredictable as well, even though these forecasting algorithms are quite advanced these days, but there are some uncertainty sorry, around that, and these kind of complicate our balancing on supply and demand, and often we face with different frequency issues in the power systems. So on the supply side, we have these complicated supply demand balancing issue, but there's also another issue on the planning side, because with this decentralization, it comes we have self-consumption. People are consuming their electricity that they are generating, and sometimes they are injecting energy back to the grid, so we have bidirectional power flows. But our traditional power systems are not designed to handle this sort of evolution, I would say, because most of the, especially in the low voltage side, are not designed to accommodate bidirectional flows. Even if it can handle bidirectional flows, the problem is that we have new forms of load being connected, for example, like electric vehicles or let's say heat pumps and these sort of things. They're consuming a lot of electricity, and with solar PV, they are generating a lot of electricity, but most often than not, they are not coinciding on each other. So that means the load shape in the low voltage side becomes with year going on, it becomes kind of the well-known duck shape. We call it like duck curve. We have a peak in the morning and a peak in the evening and a very huge valley during the midday. But power system traditionally needs to be designed to accommodate the peak demand, even though peak occurs only for a few hours annually, maybe less than 5% of the time annually. But power system needs to be designed, the equipments and assets needs to be designed to accommodate that peak demand. So the graph here kind of shows, like, as you can see, if this is our base load and if this is our peak load, which occurs only for less than 5% of the time annually, but our power system needs to be designed to accommodate that. So that leads to an over-dimensioned power system, less utilization factor of our power system. That means much inefficient use of public taxpayers' money, because taxpayers' money is being used to establish these assets and enhance these assets. In addition to these, we also have some other problems. For example, due to lower controllability on the power generation from renewables, the base load generator more often than not need to go to inter-hour cycling, which kind of affect their life cycles. And in addition to that, the trajectory has been quite erratic for renewable integration and also changes in the load shape in the low voltage side. That means the grid and generation capacity needs to be expanded and enhanced almost periodically in every few years to accommodate peak demand, and which obviously isn't feasible financially and obviously and technologically as well. So the major two problem is that we have complicated supply demand balancing on the supply side, and on the planning side we have over dimensions power system because of the introduction of the renewables and decentralization of these renewable energy sources. And these in turn increase the cost of the all parties involved, even to the downstream small scale residential consumers. So that increases your electricity tariffs. So we need more flexibility to maintain a cost-effective and reliable power systems. Traditionally, power systems, the flexibility was something that traditionally been reserved on the supply side, but with more and more renewables coming in, the flexibility in the supply side is stressed to the limit. So then it comes to the demand side flexibility options. So in last few decades, we have been seeing the emergence of this demand side management to utilize demand side resources as a flexibility option, especially when supply side flexibility is stressed to the limit. So these demand side flexibility utilize the grid is energy resources, for example, solar PV system, rooftop small scale solar PV system, battery storage, electric vehicle with a vehicle to grid or vehicle to grid building functionalities, or even controllable loads, for example, aircon, heat pump, these sort of controllable loads. These can be used with the support of advanced ICT infrastructure of our smart grid to facilitate and to support and to provide more flexibility to the power system. So we can have a peak savings program, or valley filling programs, or to smoothing the load profile of the overall load profile of the power system, so that our supply demand balancing is much cost effective. And probably the main key enabling demand side management technology is the demand response, you might know. So I'm almost sure that the audience here is quite familiar what demand response is. I'm not going to spend any time on it. It's just I have a list of most common demand response program on the right that I have here, because I'm going to refer back to this list a few slides after. These demand response programs, be it a price-based program or an incentive-based program, it basically looks into utilizing the flexibility from the demand side, either directly by a price signal or indirectly via incentive signal or a market-based mechanism. And you can capture this flexibility from the demand side to address different grid issues. For example, enhancing supply-demand balance or any critical grid problems like outage or this sort of things. So this is one of the typical solutions to solve the unpredictable nature of renewable generation and uncontrollability of renewable electricity. But in addition to that, we also have some problem emerging in the low voltage side of the network. For example, this supply side load balancing problem can easily be done by demand response programs, but demand response itself cannot handle or cannot address underlying capacity issue in the low voltage network. So I'm going to take a few slides to explain this phenomenon. So for example, let's say we have a typical residential demand profile here. Represent a typical Australian detached house with a peak around, let's say, 3 or 4 kilowatt happening in the evening, obviously, and there's a small peak in the evening. But with that, if this house is equipped with electric heating system, or obviously for winter to provide heat, that's gonna consume more than the peak demand of the house in the evening and night hours. So that's gonna increase our peak, both the evening peak and morning peak, also in night valley as well. And on top of that, if the house owner decides to install a solar PV system, let's say a 5 kilowatt solar PV system on the roof, without any battery storage system, that's going to generate around, let's say, 4.5 kilowatt peak during midday, and it's going to introduce a valley in the midday. And after a few years, if this house owner decides to buy an electric vehicles, and traditionally or typically a typical owner of electric vehicle would charge his vehicles whenever he is home. So if he is home in the evening, let's say 6-7 p.m., he plugs in his car and it starts charging at that time around 6 p.m., let's say, and it's going to consume at least 3-4 kilowatt extra if it is charging for, let's say, even in a level 1 or level 2 charging. So even in level 1 actually, so 2-3 kilowatt or 4-5 kilowatt extra. So that's going to increase our peak to almost 10 kilowatt. So where let's say a few months ago his peak was around 3 kilowatt in the evening and 3 kilowatt in the morning, and during midday it was around 1 kilowatt or something like that for base load. But after a few months later, when he installed an electric heating system and rooftop PV and an EV, his evening peak becomes much higher and his midday value becomes much lower. So it's a kind of a very high enhanced dark shape load curve for a single consumer, obviously. So if you aggregate these sort of shapes, this sort of load demand for thousands or let's say millions of consumer, what it means in the supply side is that we need more generation in the evening and we need less generation during the midday. You can say that this can easily be enhanced by some demand response program. This can easily be solved by some very flexible power generation sources. But the major problem is on the localized issues, the localized problem in the low voltage network, because that evening peak and that morning peak kind of overload the local transformer. And in addition to that, if you have solar PVs, let's say along a street, if a multiple house owner decides to install solar PV without battery and they are injecting electricity back to the grid during midday, the voltage would be rising, and along the feeder after a few hundred meters from the transformer, we're gonna see an over voltage issue. And the same thing happening during in the evening when, let's say, 20 EVs are connected at the same time in the grid, they're consuming 5 kilowatt each. So that's gonna cause an under voltage issue a few hundred meters or maybe a few hundred meters after the transformer. So that's the major two issues we have in the low voltage side. We have overloading of the transformer and also the overloading of the assets. For example, like cables can be overloaded as well. And we have these over voltage and under voltage issues because of these solar PVs and emerging forms of load, such as EVs and heat pumps. So these localized issue cannot be solved using typical demand response. That's the main problem. So yeah, this is kind of like summarizing what I've been saying. So for example, if we look at the demand response program, these are the most commonly used one. So IC service or demand bidding, these are not typically uh, provided or available for small scale residential consumer. That means these are not available in residential suburbs. The consumer in the residential suburbs cannot participate in this program. So these two are done, not available. If you look at the price-based program, for example, time of use, real time or critical peak, or even a rebate programs, they kind of more focus on solving system level issues. For example, these evening peak can be addressed if the price is higher in the evening. So maybe most of the user can adopt this price-based program and curtail some of the load in the evening and shift them to the other periods of the day. And it can it can solve the issues in the system level, but in the local level, the over voltage and transformer overloading issues might still be there if substantial amount of user decided in a particular local area decided not to participate in these sort of programs. So this is the problem with typical time-based program. They are even though they are indirect program because they're influencing by a price signal, and if consumer is not interested, or if consumer is not opting for these programs, that means you don't have any flexibility to solve this localized issue. And if you move into probably this one is the most suitable one to address localized grid issues, direct load control. Some DNSPs in Australia are trying to address this local problem using direct load control, especially by controlling, let's say, pool pump or aircon. But the main issue here is the privacy and controllability and authority. So as a consumer, you might not want a DNSP or some other third party to control your aircon in a hot sunny day, or maybe you don't want anyone else to control your pool pump, let's say at a particular time of the when you might be using your pools. So these are the kind of things that raises concern around direct load control mechanisms. That's why it's not very popular in most regions of the world, especially if you look at the Europe. They kind of discarded these programs long ago because of the privacy issues and consumer authority issues. Then we are left with is market-based mechanism like capacity market, emergency DER programs, or even demand bidding programs. This market-based mechanism can solve this issue if they are designed to mitigate local issues, but they are typically designed to address system level issues. And another problem is that incentivization framework for this market bidding program is not comprehensive, and they don't cover a lot of the aspects that is essential to incorporate and support active participation from the small scale residential consumers. So this is the main drawbacks with demand response program, and that is why the framework of transactive energy emerged as an advanced variant of demand response that can utilize the full flexibility spectrum from the residential consumer sides without affecting their profitability or without violating any of their privacy concerns or raising any of the issues that typical DR programs have. So this transactive energy framework was first introduced by Grid-Wise Architecture Council in the US, and they defined this term as a system of economic and control mechanisms that allow the dynamic balance of supply and demand across our entire electricity networks using value as a key operational parameter. This value here obviously refers to our dollar. So everything comes to a dollar value in a transactive energy framework, and the energy exchange happens dynamically over the electrical infrastructure using as a dollar value for each unit of electrical energy transacted between two parties. That can be either the transaction between grid and typical consumer, that can be in between consumer, or that can be in between consumer and maybe other SDN network operators or other service provider. Or instead of buying this commodity, instead of being energy, it can be flexibility as well. Instead of selling energy or buying energy, you can sell or buy flexibility as well under this transactive energy framework. So these are the main thing of the transactive energy. This allows consumer, prosumer, and producer of electrical energy to negotiate and trade electrical energy and other flexibility among them without affecting or without violating any of the underlying grid capacity issues. And the market framework for the transactive energy can be specifically designed to solve the localized grid capacity issues. That is the main advantage of transactive energy over typical demand response or any other demand side management programs. But the problem is that the transactive energy is quite new. Obviously, it still is in infancy phase, and there have been a limited implementations of transactive energy, and there are some pilot projects in Europe, in US, in Australia as well. But most of these basically look into for a large consumer, or even if they are allowing small scale consumer to participate in transactive energy framework, they are allowing them to participate via some sort of aggregator. The problem with aggregation is that if there is an intermediate entity between the consumer and the transactive market, that means it might affect the profitability of the consumer and also raises the same issue of the DR has response has like authority, autonomy of the consumer, this sort of things. So this is why the transactive energy management system for residential consumers needs specific attention, and the framework needs to be tailored to suit low voltage network capacity issues, low voltage network constraint, and also the objectives that can be somehow in some cases conflicting as well. The conflicting objectives of different parties involved, like consumer, prosumer, network operator, third-party flexibility service provider, or retailer, or energy service provider. Any entity can be participating in these sort of frameworks. So I have a basic illustration of how it look like for a residential network. So, for example, if you have two houses, one who has some DER and who has installed an energy management system, another house which has obviously some excessive load and also have some energy management system. At any particular time of the day, these house might need some additional energy that the owner wants to buy, and these house have some excess energy that the owner wants to sell. Instead of selling it directly to the grid and for this house owner from buying it directly from the grid, they can trade this energy among themselves, which is most commonly known as the peer-to-peer energy trading. The peer-to-peer is one of the key form of transactive energy trading. So these energy transaction can happens, and this can be facilitated by a local transactive market. So there might be a market operator, or it can be cleared in a distributed fashion as well. So if the market is cleared, then for this market operation, these two buyer and seller, they will be actively negotiating how much energy they want to buy or sell, and at what price they are willing to buy or sell their energy. And any excess energy that is not traded in the local market needs to be balanced with this upstream electricity power grid. And for that, you need an interaction with the upstream electricity market as well. So this local electricity transactive energy market needs to engage or collaborate with upstream power grid and upstream electricity market. That's one of the key feature of transactive energy for LV networks. So if we look at the key major challenges or main functionalities that you need to have for an effective transactive energy management system for low voltage residential network, there's two major aspects. If you look at here, one is the market. There is a market here, and there is a system for transactive control. So whatever market decides the energy transaction for a particular time of the day, then we need to have an advanced energy management system or load control system which can carry out this control signal coming in from the market and effectively alter or modify the consumption or generation of this house according to the market control signal. And also these transactive control or energy management system needs to be intelligent enough so that it can automatically beat into this market to maximize the profit for this seller, and it can beat automatically in this market to minimize the cost for this buyer. So obviously there is this conflicting objective here. So the main feature, if we split it into two, so one is from the market side, another one is for the residential energy management side. From the market side, the market mechanism needs to have these four major features: autonomy, privacy, profitability, and decision making. And on the energy management side, it needs to be able to handle multi-objectivity and uncertainty. I'm going to briefly explain what each of these are. So by autonomy, what I mean is that the consumer should have the autonomy to by autonomy, I mean autonomy in terms of participation in the transactive market. They can decide to engage in any market time interval, and they can decide to opt out for a particular time of the day or for a few days aggregatedly. And so that we have spontaneous and active participation from the consumer. So the problem with autonomy is that if we have more autonomy, that means if we shift all the power to the consumer, that means some time of the day there might be limited flexibility available in the local transactive market. So that's the first problem. The second features the local transactive market mechanism is the privacy. So obviously privacy is a major concern for any consumer who needs for some of the demand response or demand side management program often need to share how much energy they want to buy, sell, or consume or supply in a particular time of the day, and that there's some concerns around that this might lead to revealing who this consumer is or how this consumer behaves, and this leads to many sorts of privacy violations. And these are even banned in some European countries to share private consumers data, even in some Australian jurisdiction as well. So that's the problem. So there's all of these are conflicting. So we need to have a system which allow privacy, but because it needs to be private, so that we are not sharing any information from the consumers, and without information from the consumer, it's really difficult to clear the market. So there's conflicting issues in there. The next problem is profitability. The market mechanism needs to provide maximum profit for all the participating party. For the seller, that means it needs to maximize its let's say selling price, and for the buyer, maximum profit, it needs to minimize the buying price. So that's the conflicting decisions there. And the next one in the market mechanism would be decision making. So the transactive market needs to provide consumer with decision making authority. So they would be the sole authority who is making decision when to shut down, when to turn on and off their aircon, or when to control their electric vehicle charging, or let's say solar PV generations. And in the energy management side, we have two problems. One is multi-objectivity, and the one is uncertainty. What I mean by multi-objectivity is that if you are a typical residential consumer, let's say you have some distributed energy resources, let's say you have a solar PV system, you have a battery, you have an EV, you have an aircon which can be controlled. So by default, if we want to minimize your electricity bill, that would be your main objective of your energy management system, to reduce the electricity bill. But how it reduces the electricity bill, it controls your controllable devices. For example, it control your storage devices. Battery storage system are going through rapid charging and discharging cycle, so that it can charge us more and store energy when grid price is cheaper, or when you have more solar, and maybe discharging this electricity back to the house or even to the grid when electricity price is higher. So this leads to degradation of the storage devices, and you need to minimize that storage degradation. The next thing is, if you have an air con or any other thermal load, and if you're controlling that to minimize your electricity cost, that means you are kind of leveraging your thermal comfort, and that thermal comfort needs to be maximized for a typical consumer for the energy management system. And another thing is that if you are kind of shifting any load in a different hours, different time periods of the day to reduce electricity bill, so that kind of creates some inconveniences. For example, if you have an electric vehicle and if you want to charge it in the evening, but due to the higher prices, your energy management system decides that it's better to charge the vehicle at night, at let's say 2 a.m. at night, in the morning, something like that. But if you do not want to do that, what if you have an emergency call later 11 p.m. at night, you need your electric vehicle? So there's some inconvenience there, and that inconvenience needs to be reduced or minimized by this energy management system. So these are the multiple objectives your energy management system needs to handle. And in addition to these multiple objectives, there is some uncertainty. So all of these energy management system in the residential buildings, they schedule building loads or energy resources. If they are scheduling it in a day ahead, that means there is a deterministic scheduling, and this deterministic scheduling kind of use forecast information. And in forecast information, there's some uncertainty around that. For example, you don't know how much solar PV you are going to generate next day. You don't know what would be the spot price of the electricity you are buying. You don't know if your electric vehicle, when you're returning from home, at what particular time you would be returning home and plug it in, and how much it SOC be. So these uncertain parameters increases a lot of vulnerability. It introduces a lot of vulnerability to your energy management system, and an advanced energy management system for a transitive energy framework needs to be able to handle this uncertainty. So I'm gonna
Just give you like a pause now.
stop here for a few moments, and if you have any questions.
So is anyone have got any question or comments?
Are there any questions?
I hope you understand, like,
And some people are actually aware of this topic as well.
Your voice is again, breaking down.
Same thing here as well. I couldn't actually hear all that properly.
But anyway, what I was trying to say that, what Saurabh, I think, did explain in very details, and also I think he's going slowly. So I hope everyone has understand, like, what are the challenges. First thing, like, what is transactive energy management? Like, why we need transactive management? If you compare with demand response, and then he has also talked about, like, different challenges that need to be addressed. For implementing transactive energy management in the real system.
Yeah.
So does it make sense to all of you?
Sure.
Yes. Okay.
Only one thing I have.
What I was saying was many people are not related with this topic. So that is why.
Sir,
Yes.
hello.
Yeah, we can hear you.
Sir, actually, I have only one doubt with respect to sort of presentation, sir. So he was telling transactive energy is like when we transfer energy from one residential, which is acting as a source, and another residential is acting as a residence is acting as a load. So the transaction of energy between these two residential loads, will it be legally possible, sir?
Yes, it would be. So there are many pilot projects which are going on around the world, and I don't know if you heard of the Brooklyn microgrid. So there's a huge microgrid system in Brooklyn, USA, and they implemented this peer-to-peer trading system. And so basically, so there's a cloud-based system where you can submit bid, how much you want to buy and how much you want to sell at what particular price. And there's some market trading going on, just like how stock markets work. So just like stock market, you are submitting your bids and offer, and these bids and offer are being traded in these cloud platform to facilitate peer-to-peer trading. So the problem is that if you are trading energy between these peers, for example, one house to another house, you are using public grid to supply this electricity from one end to another end. So that is why you need to pay some charges to the network operator. But you are not buying electricity from the retailer, so you don't need to pay anything to the retailer.
I think in USA, Virginia, I mean, they also have like an implemented, transacting energy management concept for a local microgrid. So that's, implementation has already been done, in some countries for like a small level, like the microgrid level.
Okay.
May I
There
add
are a lot
something?
of policies related, isn't it, sir? Thank you, sir.
Am I audible?
Yes.
Hello.
Yeah, we can hear you.
Yeah, actually, Professor Chillamal, there is one project in India also, in Delhi. If you just search off, you'll find one blockchain-based peer-to-peer energy trading in Delhi. They have started it on a pilot project basis, and in which you can sell electricity to your neighbor.
Okay. Okay.
Believe it or not, we actually have this system implemented in Bangladesh as well. So me and Professor Jahangir, both of us are from Bangladesh. In a rural area, we have an off-grid microgrid system, and a company called SoulShare who actually install solar panel on the rooftop, and they install a SoulShare box, which is connected to the internet, and these houses trades an electricity among each other using their proprietary cloud-based system. So this is essentially a peer-to-peer trading happening in a very rural village in Bangladesh.
Oh, thank you, sir. Thanks for the information.
Yeah, Saurabh, you can continue.
I think I can,
There-
yeah. So yeah, this is, yeah, I can understand now that some of the audience might not be quite familiarized with the concept. So that's why I wanted to spend some time on the background to discuss through what transactive energy is and why we need this sort of framework other than typical demand response framework. What is the problem of this demand response framework? And if we want to have implement an effective transactive energy management system, we need two things. One is an effective market mechanism. Another one is a residential energy management system, which is capable of handling this energy transaction between neighbors or with the grid or with any other party. So, and there are some challenges that I was discussing. This market needs to have all of these four features, and the energy management system needs to be able to handle multi-objectivity and uncertainty. So I'm going to present a few case studies that I've been working on to design transactive energy management market framework and energy management framework to facilitate local energy trading and to facilitate not just energy trading flexibility as well. And I'm going to explain in a bit what this would look like. Yeah, I think I do have links to the publications as well if anyone is interested to have a look. So the first case study I'm going to discuss through is a development of a residential home energy management system to support energy trading in a transactive energy framework. So, yeah. So this is basically focusing on the residential energy management side. It's not so much on the transactive energy framework market side. So because I want to go like bottom up. So first thing is, if you have an energy management system that needs to be able to support multi-objectivity and that needs to address uncertainty. So multi-objectivity means there are 4 conflicting objectives: reduce electricity bill, reduce storage degradation, maximize thermal comfort, reduce user inconvenience. And uncertainty is there are some uncertainty in the prediction, in the solar generation, in the electricity price, these sort of things, and how to handle this uncertainty. The energy management system needs to be able to handle this uncertainty. So the main objective of this case study is to develop a comprehensive residential home energy management system that is capable of incorporating flexibilities of various controllable residential loads and distributed energy resource unit to minimize cost for the consumer, considering multi-objectivity and uncertainty. Right? So I already explained what this multi-objectivity is, and I already explained what this uncertainty is. So the main contribution of this research work is that we developed an algorithm for home energy management system that is capable of handling this multi-objectivity and uncertainty without violating any of the user constraints. And we developed a comprehensive mathematical model to represent multi-objectivity, to represent the degradation of the storage unit. We develop a mathematical model for that. We develop a mathematical model for the thermal model of a typical residential building, to how to estimate the thermal comfort of the consumer. And we also formulated a bidding mechanism. So remember, if we go back to this slide, your home energy management system needs to bid to this market, in this market, they need to submit how much energy they want to buy or sell and at what price for any particular time of the day. So this energy management system that we proposed is capable of it incorporated with a bidding model, so that it can determine optimally what would be the maximum allowable energy to be sold or to bought from this market, and at what price, without without violating any constraint and with satisfying multi-objectivity and uncertainty. So I am going to explain the mathematical model a little bit. So for example, if you have some time shiftable load at your home, for example, washing machine, cloth dryer, and dishwasher, some of these advanced, for example, the washing machine I have at my home or dishwasher that I have at my home, we have this time setting, so we can just load in with our dirty clothes or dirty dishes and put in a particular time. We can, instead of setting that, okay, I want to turn it on right now, we can give it a window. We can say that, okay, I want to run it between 6 p.m. to 10 p.m. and it's going to take maybe 30 minutes or an hour to complete this operation. But instead of directly setting when to turn it on, I set a window of operation. And within this window of operation, my home energy management system would automatically decide which time slot is the optimal one, considering all the objectives of the consumer to satisfy user constraint. So that's the thing. So we have this time shiftable load, and if you don't satisfy this consumer's objective, that means this is introducing some inconvenience. And for example, if you have washing machine or clothes dryer, and if it is already turned on, for example, let's say you set a window of 6 p.m. to 10 p.m. At 8 p.m., it decides that, okay, this is good now because the price is lower and I have some energy stored in my battery. Let's turn on my dishwasher. So I turn on my dishwasher at 8. Actually, the energy management system automatically turns on the dishwasher at 8 p.m. And after 20 minutes or so, when this is, let's say, here in the operation, there's some critical issues in the grid. The electricity spot price jumps through the window. It jumps from, let's say, the price jumps from, let's say, 20 cents per kilowatt hour to maybe 80 cents per kilowatt hour. Or maybe, let's say, I ran out of my battery, or I need something else to run my battery. So if you turn it off now, that means, sorry, if you turn it off at this stage, that means you have to turn it on again after a few minutes. So these energy that the dishwasher has already consumed, that's going to be a total waste. So if you do that, that's going to introduce an inconvenience there as well. And the objective of the optimization problem is to reduce this inconvenience, minimize this inconvenience. So we mathematically represent that by a penalty factor. So we have the interruption penalty coefficient, and this binary variable y captures at a particular time if the device is on and off, if the device is turning on or off from an idle state. So for example, whenever a dishwasher decides to turn on at this particular time, the value of the y will be 1, and it captures all the values of y. And whenever it is more than 1, that means it is turning on at least twice a day, but we only need it once a day. So there's going to be introducing a new penalty, and that CINT would be the cost of this interruption penalty. So that is how we mathematically represent this user inconvenience. So next, we have a mathematical model for the storage system. So let's say if you have a battery storage system, or let's say you have an electric vehicle which you are charging and discharging to reduce the electricity bill. So if you do it like this way, so for example, let's say your price is going up and down, is fluctuating. And for that, the battery, so this line here represents, this is idle state, this is charging, and this is discharging. Let's say at 4 a.m. it starts charging for a few hours, then it idles for 15 minutes, and it goes back to discharging. Then it comes to charging, discharging, this sort of cycles, because this is the most optimum one considering the electricity cost. But by doing this sort of operation, what it does is that it is going through frequent charge and discharge cycle, and that affects the life cycle of the battery. That reduces the total cycles that the battery can go through in its lifetime. That's going to degrade the battery, then introduce a degradation cost. But instead of that, if we do something like this, if you charge this for a few hours in the morning and then do not use it throughout the day and only discharge it in the evening to reduce the peak demand, what happens is that it doesn't degrade the battery that much, but we are not using the battery to its full capacity, and we are losing some of the money, because by doing this charge discharge cycle, you are earning a lot of money. Actually, you're saving a lot of electricity bills. So there needs to be a trade-off between these two. We need to have a middle ground between these two, so that you get optimal electricity cost and optimal degradation of the battery. So for that reason, we need to mathematically model this storage degradation. So we have this equation here represents the SOC of a battery. Then from the SOC, we can calculate the depth of discharge of a particular battery, obviously 1 minus SOC. And for a particular time of the day, if we can calculate the depth of discharge of a battery, from the depth of discharge, we can calculate the cycle aging degradation using near quadratic equation, near quadratic DOD stress function. So based on the DOD, it's gonna introduce a marginal degradation cost, and that marginal degradation cost is calculated through the overall degradation cost using this equation. And so this cost function is for cycle aging degradation. In addition to the cycle aging degradation, so this function is multiplied by the replacement cost of the battery, and that gives you the actual cost term of degrading this battery for going through a charge and discharge cycle. And in addition to this storage degradation for the DOD stress, we also have cycle degradation. If it is going through charge to discharge and discharge to charge quite frequently, for example, if you look at here, charge to discharge and discharge to charge, and then again jump back to discharge. So instead of doing this, if we can put these two discharge one after another and put these two charge one after another, that might be better from the cycle aging or the cycle lifetime perspective. So to represent that, we have this Boolean expression that capture when this X value and Y value, this captures charge to discharge. And this Boolean expression captures whenever a storage device is changing its mode. And for any mode change, it introduces a penalty coefficient, and that is converted into a dollar value by this penalty coefficient. And so this cost here represents the cycling cost or cycling degradation cost, and this is the aging degradation cost. Then we have a thermal model for the building to capture the thermal comfort cost of the user. So for example, let's say if you have an air con or if you have a heat pump in your house, and so what you can do is, okay, no, I don't have it. If you can set a fixed temperature, let's say in a typical winter day, let's say, or let's consider a summer day, because summer the temperature outside is 40 degrees Celsius. You want your aircon to be running at 18 degrees Celsius. If it is fixed at 18 degrees Celsius, that's okay. But instead, what if you fix a range? What if you just say that, okay, I want it in between 18 to 20 degrees Celsius? Then you fix the range. So if it is fixed at let's say 18 or less than 19 degrees Celsius, let's say this is my consumption. If it is running throughout the whole day, this is actually run for actually heat pump for the heating. So if it is running for a typical winter day, so if it is running for the whole day, this the red lines is actually the power consumption for the heat pump. But instead, if you put a cycle, if you put a range, let's say a range of temperature that you want to operate in, so instead of going a flat line, it's gonna consume some energy, so that it increase your indoor temperature, and it's gonna start like reducing its energy consumption to down to almost 1, and let the indoor temperature to fall down. But if it is falling down to the lowest threshold, then it starts picking up electricity again, so that your indoor temperature remains within your threshold level. So for that, we introduce a thermal discomfort cost. So if, let's say, if you have a flat line of temperature, there's let's consider for a winter day, let's say if you want your indoor temperature to be 25 degrees Celsius, but if it is going up and down, up and down, and up and down, so for any changes from 20 degrees Celsius, there's gonna be a discomfort. So these changes is captured here, and with that changes, you introduce a penalty factor that gives you a dollar value for this thermal discomfort. And this indoor temperature is calculated. This indoor temperature is calculated based on a thermal equilibrium model, which is based on this equation. So any heat in to the house and any heat out from the house needs to be equal in a thermal equilibrium. If you consider an isothermal mass of air, and with basic thermodynamics, we model it mathematically, and based on that, we got the value of theta, which is the indoor temperature, and from that we calculated this dollar value of thermal discomfort cost. So now that we have all the costs, so we have an equation for the energy cost. So this is the equation for the energy cost. Let's say if you want to, P plus is energy buying and P minus is energy power selling, and lambda plus and minus is the price for electricity buying and selling. And let's say this is your energy cost, and let's say these bar value represents the prediction in day ahead. So let's say you know for sure how much your electricity price would be at a particular time of the day. So if you know it for sure, we can just use this deterministic scheduling, but there's going to be some uncertainty in the electricity price. That uncertainty is represented using a Monte Carlo simulation. So using Monte Carlo simulation, we generate a huge number of scenarios of how uncertain these electricity price can be. And for all of this scenario, we calculate the real-time imbalance cost, and that real-time imbalance is traded using an imbalance tariff and imbalance power. And these here represent the probability of each of the scenario in the Monte Carlo. So this is our total electricity cost. So we have this energy cost that's subject to an energy imbalance equation. This is our energy imbalance equation, and this is true for both real time and day ahead as well. And these cost minimization needs to be subject to minimization of our interruption cost that we calculated before, needs to be subject to minimum thermal discomfort cost and minimum battery degradation cost. So our optimization model looks like we have an optimization objective on the top, and on the bottom we have 3 more optimization objectives. So this looks like a bi-level optimization problem. So we have an upper level. So this is our upper level main objective problem, and we have 3 lower level optimization problem. So problem with this sort of bi-level optimization problem is that it takes a lot of time to solve this problem using commercial solvers. Actually, it took more than at 24 hours to solve one single problem for a small household. So we need to simplify this problem. So what we did is that these lower level optimization problem, there are some binary constraints there, and these binary variables, we applied binary decomposition to linearize that. So we have continuous equations here in the follower problem 1, follower problem 2, and follower problem 3. But in the follower problem 3, not just binary, we also have a quadratic equation. So that quadratic equation, we first applied piecewise linearization. So we have binary linearization, and on top of that, we apply binary decomposition to get to a continuous equations here. So we have 3 continuous followers objective equations. So that gives us equilibrium problems, and we took the first order KKT conditions of all of these equilibrium problems and added to the main objective function. Then it becomes a single level optimization objective with continuous variable. There's some binary variable here, but there's no binary variable here. So our overall problem becomes a mixed integer linear programming problem, where it was previously a bi-level non-linear integer programming problem. So we solved it using GAN software, and we could solve it within 4 or 5 seconds for a whole 24-hour day with 100 Monte Carlo simulations. So, and the uncertainty associated here, we represented as the two-stage stochastic optimization. So we have both bilateral optimization here, and we also have stochastic optimization here, which is again converted into a single level mixed integer linear programming problem to solve more efficiently using GAMs. So we run some simulation. We ran the simulation for a week actually. We did the simulation for a 2-story duplex Australian house with an approximate floor area of 250 square meter. We have considered a washing machine, dishwasher, a pool pump, a heat pump as a flexible load. We considered a 6 kilowatt rooftop solar PV system with a Tesla Powerwall 2 battery, which has a capacity of 14 kilowatt hour. We consider that this house is equipped with electric vehicles, a BMW i3 vehicles with a 94 amp hour lithium ion battery. And we use artificial neural networks for forecasting the solar PV generation based on historical load data, historical PV data, and also same for the load demand and market prices from the Australian wholesale market prices. We use ANN for the forecasting, and based on the forecasting, we applied Monte Carlo for generating, first generate 1000 scenarios. And out of those 1000 scenarios to calculate efficiently, we reduced the scenario to 100. So we used a scenario regression technique to eliminate the scenarios with lower probability. And then on top of these 100 scenarios, we added, we consider their probability as equal. So 100th probability for each of them. And we added that to our stochastic optimization problem. So these are the some of the input values we used. For example, this is for solar PV, and this is for household load demand. So the yellow here represent the scenarios, the red is the actual consumption, and green here, blue here is the forecast value from the ANN. And with that, so this is the results we get for the bidding. So for example, if you can see, there are two types of bid. One is the red ones is the day ahead bids, and the other one is for the real-time bids, and yellow are the scenarios one. So as you can see, there are some positive bids and negative bids. So positive bids meaning that this is obviously bidding to buy energy from the transacting market, and negative bids, this is bidding to sell energy in the transacting market. And if you look at the temperature here, indoor temperature, the black line here, black fluctuating line represent the indoor temperature. So theta set was the red line, and as you can see, it's fluctuating around the set temperature so that our thermal comfort level is maximized. And for EVs, as you can see here, that black solid line here is the time when EV is not at home. So we put a constraint that EV needs to be charged at least 70% at the time of the departure. And whenever EV is arriving, it instead of start charging immediately, it actually discharges a bit in the evening, so to supply some of the demand in the household so that our electricity bill is reduced. And then again, it pick up energy at night, specifically when wholesale price is lower, and it starts up to the at least 70% for the next departure. And we also introduce some sort of irregular thing on the weekends, like Saturday and Sunday. Instead of showing typical work day for Saturday and Sunday, we consider that, okay, the owner might be going out for a few hours in the evening instead of going out in the morning. So our model can handle these sort of things as well. So as you can see here, we have a table here. This is we compared our proposed scheduling strategy with a number of state-of-the-art method. So strategy one is inflexible strategy. That means without any optimization, we are just doing rule-based scenarios. Whenever PV is available, is storing energy to the battery, and whenever EV is available, it's just consuming electricity to increase the battery capacity. That's it. And the strategy two is the deterministic scheduling. That means we don't consider any uncertainty and any error in the forecasting. So no Monte Carlo simulation, and we do it in bi-level optimization. And strategy three is a single level problem, but we consider the uncertainty here. So here we consider uncertainty, but not multi-objectivity. And here we don't consider multi-objectivity, but we consider uncertainty. And number four is a single level problem, but multi-objective problem. So instead of representing multi-objectivity as a bi-level problem, we can also do it in a multi-objective fashion. So strategy four is for multi-objective. As you can see here, if you look at the, I'll just gonna go to the total cost. If you look at the net energy cost, so out of these four strategy, so our proposed method is the cost is lower compared to the all three, but the cost becomes higher compared to strategy three. So if you look at the strategy three is a single level problem, that means we are not considering uh, any storage degradation cost or thermal discomfort cost or inconvenience cost. If we add them up, if we have a storage degradation of $64, thermal discomfort of $32, and interruption of $5, is gonna be more than a combination of these two. So obviously our proposed method outperforms all the available state-of-the-art energy management algorithms, to be honest. So we done the simulation for 7 days, both for the summer and winter week, and in both cases, it outperforms typical methods. So yeah, I think I'll better if we just stop here for a moment if anyone wants to ask anything.
Yeah, I mean, probably it's a good idea. I mean, although, I mean, I'll mention, like, many of the audience, they don't have this background, but I think the way that, I mean, you have presented, it looks, I mean, for me, I mean, it's not that difficult to understand, like, and also, like, I know that many of the attendee, I mean, they are interested for like the battery. So, I mean, you also explained the detailed battery modeling, even including degradation. Many of the existing battery model, I mean, they don't consider the degradation. And also, like, I know that many of the attendees, they are also quite interested for like learning how, I mean, optimization can be applied to solve many of the power system problem. So is there any question, comments for like the application or example that Saurabh has shown here?
No, I think maybe we can move on. So
No, I don't think there are any questions.
yeah, sure, no worries. So yeah, I'm happy to share the slides with you if you are interested, and I do have the your citations for the papers which you have detailed descriptions of the model and results. So if you want to have a look, maybe you can go to the publications if you're interested. So probably you can go move on to the next case study. So this one here is to design. So once we have developed an energy management system for the buildings, so next to move on to the neighborhood level. So how to design a market so that this some buildings which are fitted with this energy management system can trade energy among themselves and can also maybe buy or sell or trade something else as well. So this is the overall architecture. So we develop energy management framework for a residential neighborhood based on multi-agent system. So I'm not sure if any of you are interested what multi-agent system is. It's kind of representing all the entities in a physical system by a software agent. And we developed this multi-agent architecture in a Java environment called JADE, Java Agent Development Environment. And so we have, for example, if there is a house, this building is represented by a building agent, and within this building, if there are multiple devices, for example, by devices we mean flexible devices, let's say dishwasher, washing machine, these are flexible loads, these are devices, solar PV, battery storage, PVs, EVs, these are devices, and each of them are represented by device agents. And within this neighborhood area, there is a local transactive market, which is coordinated by an agent called local transactive agent. And this neighborhood is supplied by a local transformer, distribution transformer. And obviously this transformer is owned by the local network operator, and this network operator or grid is represented by an agent called grid agent. So each of these agents has their own particular objective. For example, this device agent, they want to operate their particular device with its own objective. If it is a storage device, if it is a battery agent, the objective would be to run the battery more efficiently so that its degradation is reduced. If it is a aircon device agent, the objective would be to run the aircon so that the thermal discomfort is minimized. Same thing for if it is the building agent, the objective would be to minimize all the costs, to minimize electricity, thermal discomfort, and everything. And if it is the local transactive agent, the objective would be to uh, clear the market such that the profit for all the consumers within the neighborhood in the market is minimized. And if it is grid, the objective is that the grid constraint is satisfied in any market interval. That means the transformer is not overloading any hour of the day. That's the objective of the grid agent. And if a particular time of the day, let's say a transformer is overloaded, let's say transformer, let's have a take a toy example. Let's say that this transformer has a capacity of 100 kilowatt peak. If all of them are consuming a lot of energy, and at a particular time the transformer load is let's say 120 kilowatt, so that extra 20 kilowatt, this grid agent will be sending a signal to this LTA asking, hey, my transformer is overloaded by 20 kilowatt. can you see if you can give me this 20 kilowatt? So where this 20 kilowatt would be coming from? So these LTA would be broadcasting a signal to this building agent saying that, okay, there is a request from grid agent saying that if any of you are willing to reduce your electricity, and our target is to reduce 20 kilowatt. So what these building agent will do is they would bid in this transitive energy market how much each of them are willing to reduce in terms of their consumption, and what would be price for that reduction. All right. So this is one sort of transaction that can happen between consumers and between the grid agent. There can be another scenario. For example, these building agent instead of decided that there's a two-stage market. In the day ahead, this decides that, okay, I want to, at a particular time of the day, I want to buy an X kilowatt hour or less X kilowatt hour electricity. But for some reason, it needs more now. It needs instead of let's say instead of 3 kilowatt, it needs 4 kilowatt, 1 kilowatt hour extra electricity this building as a need. So instead of buying it directly from the grid or public in the wholesale trading price, which is much higher at that time of the day, what it can do is it can send a signal to these LTS asking that, okay, I want to buy 1 kilowatt hour from my neighborhood. Is anyone in my neighborhood is willing to sell it? So instead of going directly to your neighbors, you submit that bid to this market, and your neighbors will be submitting their offers. For example, this one will say, well, I cannot give you 1 kilowatt, but I can give you 500 watt at 20 cents per kilowatt hour. And these guys, I can give you full 1 kilowatt at 35 cents per kilowatt hour. So there will be a lots of bid coming in from all of these building agents, and these bids will be calculated based on the home energy management system. So these sort of bids, the home energy management system will decide these sort of bids, and these bids will be coming here, and this LTA would be clearing the market. So we have this day-ahead scheduling problem model. This is exactly the kind of the same that we had before, which by itself can reduce 23% of the electricity cost. And on top of that, if you have some sort of trading, so there will be a demand bid submission, and there will be some transaction request, and the seller would be submitting their submission bid based on an optimization problem. And if the bids are something like that, so if they say, let's say the required transaction amount is this much, and these are all of their bid stacked on top of each other in a in aggregated fashion. So if the requirement is this one, so all the bids up to bid 6 will be accepted, and they will be paid at the maximum tariff that bidder 6 said, which is lambda B6 lesson. Same thing for the, if let's say our transaction requirement is this much, but we got bid up to this much. So this remaining balance would be purchased from the national grid at traditional retail price. So that's the kind of the interaction we have with the typical grid as well. So with this, we ran the simulation, and we did the simulation for a whole year actually, from January to December. So because we wanted to see what sort of things would look like, and we did this simulation, I think, let's see. It was around 42 consumer in residential suburbs with 100 kVA and 100 kilowatt capacity transformer, and this feeder was overloaded some times of the day, and these are the overloaded scenarios look like. And during this transformer overloading, the grid agent were requesting flexibility from the users, and the local transactive market actually supported that, and that on those periods the max aggregated demand actually reduced to 100 kilowatts, so the transformer is not overloaded anymore. And this shows that an average consumer get a profit of 25 Australian dollar, even though it sounds like too small of a profit. But if you compare that, what typical solution is, as in Australia currently the feed-in tariff, like if you have a solar and if you want to sell electricity back to the solar these days, you would get only 5 to 11 cents for each kilowatt hour of solar electricity they are supplying, you are selling back to the grid. Whereas this sort of transaction, local transaction, you can get up to 49.3 cents per kilowatt hour, which is obviously 10 times, almost 10 times higher than the feed-in tariff. And from the grid side, what it means is that throughout the year, there's no transformer overloading. So if you consider a typical transformer, so if you for a whole 1 year, if you consider this 1 year, so to meet this peak demand, this transformer capacity needs to be increased by 20% to 120 kilowatt, and that would mean approximately 5,000 investment. And if you convert that 5,000, the savings we have is that, so out to solve this problem for 1 year, the grid operator only needed $223 to solve the problem for a year. That means you can defer your investment by a year if you just use $233, and that becomes a 20 years for whole $5,000. That means you can defer it by almost 20 years using flexibility from the local transactive market without investing on transformer capacity. But yes, that's oversimplification of things, obviously, because in 20 years time the load pattern will not be linear, it would be exponential, but still you can defer it at least 5 to 10 years without by using the flexibility from the local side. That's the main benefit of this sort of transactive energy trading. And yeah, and these results and methods, everything has been published in a journal in article Transactional Industrial Informatics. And this is the citation information. If any of you are interested, you can go have a look. Yeah, this is case study 2. I can pause here for a few seconds if anyone wants to shoot anything.
Maybe we'll finish in next 15 minutes.
Yeah.
So by 8:15, maybe,
Yeah, sure.
But is there any question, comments for the second application?
Excuse me.
Yes.
Hello.
You'd like to say something, or?
Hello, are you able to hear me?
Yeah, we can hear you.
Yes. Regarding this local, if you say the multiple houses, if it is giving to meet the 20 kilowatt deficiency of the power, when there is a uncertainty of fault, if with one particular domestic supplies, how you are capturing as a penalty, whether it is distributing into the entire people or it is only to the particular house which it is generated the fault.
We are actually not putting any penalty here. For example, if there's anything happening to this house or something, and if there's energy shortage or if there's any excess of energy, that shortage or excess of energy is actually traded in the market by the other participants.
Okay.
So instead of we don't need to penalize anyone. I'm not sure what sort of fault you are referring to. If it is like a typical, let's say this is not
That short circuit may disturbance entire distribution of that particular power, entire distribution. So with that, the effect it is it means that effect may distribute to the everyone.
Yep. So you're saying if there's any fault which is hampering supply to the whole neighborhood, something like that,
Yes.
right?
Yes.
Yes. So that would be actually not within the scope of the transactive energy because it's the market framework. So if there's any issues in the actual network, that's gonna be the responsibility of the DNSPs to solve the issues. So the DNSP is because whatever the market trading is going on, DNSP would be charging this market for utilizing their physical assets like cables and poles and transformer, these sort of things. So it should be DNSP's responsibility to solve any outage issue or something like that, if you are referring to something like that. But if there's any shortage of supply or if there's any excess generation, that can be traded within the market by this local market.
What we have considered here that while we are doing all the trading, it will satisfy all the grid constant.
Yes.
So it is not something that while we are trading energy, it is exceeding transformer capacity or even the cable thermal limit. So I mean, if something happened, that could be something, externally fault that can definitely, that can, um, you know, um, affect the operation, like powerful operation. But that's again, said that, there are some protection and other things in the network, so that will be taken care by the network operator. So that penalty definitely will not come to the customer side. So, and also due to this operation, as I said, it will not be affecting any technical, constraint in the network.
Because this one of the market clearing constraints, objective function will have network constraints like voltage violation, thermal limit violation of the line flows, and the transformer overloading violation, these sort of things. So instead of saying that, okay, instead of allowing this transformer overloading and have some sort of outage, we can prevent this sort of transformer overloading by trading energy within the neighborhood, and that comes with an additional cost of $233 for the DNSPs. So if you are a DNSP, if you want to avoid this transformer overloading, you have two options. The traditional solution is you increase the capacity to 120 kilowatt hour and 120 kilowatt, and that's going to be an investment cost of $5,000. But if you implement this sort of local energy trading, and you can trade flexibility from local market and prevent such transformer overloading for a whole year for the cost of $223. So you can defer your investment by an year by investing $223 per year. So that's a huge plus for the DNSPs, because the way the growth rate in the low voltage side is quite exponential, and it is pretty difficult to predict what's going to happen in 2, 3, 5 years time. So most DNSPs would like to wait at least 2, 3 years to invest heavily on expanding the capacity. So it would allow them to have a breathing space, and this transition will be much smoother if we have some sort of local energy trading.
Okay.
That's right. That's why, currently most of the grid operator, they are giving focus more on the demand side, not on the generation or infrastructure side, their own infrastructure. Yeah.
I think I'll just probably wrap up after one more case study. So
Yeah.
I'll probably skip.
Can I
Sorry?
just,
Yes.
what kind of hardware have you analyzed? What kind of hardware would be required for this energy trading?
Yes, I did. So I was planning to skip this one. Maybe I can just briefly touch on this one. So case study 3 is a small practical demonstration of what sort of these agent architecture would look like. Actually, we did this in collaboration with some researchers from Technical University of Eindhoven in the Netherlands. So we implemented these in a laboratory environment, and these device agents are actually physically they are represented using a smart plug, and each of them cost around 80 to 90 Australian dollar. And this HIMS agent was a cloud-based software environment. So, and this one of the building agent was represented in a simple Raspberry Pi, which is to a 200 or 300 Australian dollar. So whole setup for one building cost around 500 Australian dollars, something like that, if you have 4 to 5 smart plugs and a Raspberry Pi setup, and everything is coordinated by an aggregator in a cloud system. So it's much efficient, and because these market mechanism, this trading is not computationally heavy, we can easily do that in Raspberry Pi. We can implement the model in Raspberry Pi, and we did some practical analysis and laboratory works as well here, and the system was quite capable of doing that, even though it was done in a very short, small scale setup, but system was capable of doing this sort of complex algorithms. Yes. So
Answering your question, Altaf?
Yes. I didn't know that was coming.
No, anyway, yeah.
Yeah. So I'll probably skip this one then. So yes, something. So we did some multi-agent system here in this one, but this one mainly focusing on electric vehicles. And we also introduced that how this is not violating. So for example, we had one question before like network constant. So I'm gonna just briefly show you. So for example, if you go to aggregated load of the transformer loading, as you can see here, these this red line here is the maximum capacity, and our case 3 is our proposed scenario. So that means these two cases not violating any of the transformer overloading scenario. And if you we have the voltage situation here as well. So if we look at the traditional approach without our proposed method, so we're gonna have some sort of kind of under voltage issues here. Voltage going down to almost 0.9 per unit. It was done in small scale with just 15 houses considered to be equal to electric vehicle in a neighborhood of 42 house, and we had an maximum we got voltage, maximum voltage we got 1.05 per unit, and with our proposed method like case 3, so we can obviously reduce that to and book it aligned uh, uh, within our allowed limit. And if you look at just number of the events here, we don't have many events going on, many over voltage or under voltage events going on. So this is obviously just validating that this kind of local energy trading is not violating any voltage constraint or power flow constraint. And this is the final case study we have. This is kind of a nested framework we have. So if we have a local market, so all the time we've been talking about local electricity market. What if there are thousands of such local electricity market? Can we somehow aggregate that and trade them in a central wholesale market as well? So this is a framework for nested transactive energy markets. So we have, let's say, n number of local transactive market, and these are aggregated by local flexibility market, and these are aggregated into a mid-level thing, and which is finally aggregated to the system level wholesale electricity market. So we kind of validated that we done some simulation from considering 1 million consumer. So we did some analysis work and saying that how much their cost would be. As you can see there, I think this is for a day actually. So their reward is around 10 to 15 for when only 10% of them are participating. As they increase in participation, they decreases, but then again it increases again. Same thing for the transformer overloading. So if it is all the consumers are there, and our transformer overloading cost would be around 233 that we had before, and it would be somewhat even less when less consumer are participating. Yeah, and then we for in the wholesale market scenarios as well. So if they are aggregated into the system level, so these are all like financial modeling and financial cost benefit analysis to understand how the benefit would be for the consumer, considering their storage degradation, thermal discomfort, or any other inconveniences. And yeah, it seems like with 1 million consumer participating in such local market distributed over thousands of local neighborhoods, this can work pretty well addressing those local capacity issues, and as well as system level supply demand balancing issues. So yeah, this is to demonstrate that transitive energy can be a viable solution going forward if we have more DER in the residential neighborhoods. And there's some issues with that, is that how to incentivize this consumer for participating in this transitive energy, because current market framework doesn't allow active negotiation, even though this is happening in pilot implementation project, but it's not into the current market operation regulation here in Australia and other regions as well. And going forward, there would be this would be quite interesting, because as you can look, like peer-to-peer trading and distributed market clearing mechanism, these are quite hot topic these days in research and academia. And in we just consider voltage management and overloading management, transformer overloading management using local energy trading, and we could also introduce other services like frequency regulation, reactive power support, or operating reserve service, these sort of things, that can be easily integrated. And we also can apply advanced AI and machine learning to see how the what will be the socioeconomic impact on the consumer side, and how they would behave and model their social behavior, so that we can develop more advanced bidding algorithm for this local transactive market. Yeah, that's a quite interesting domain, and there's many different branches of future resources. And yeah, if any of you are interested in working on this domain, and feel free to reach out, and I'll be happy to discuss through in later time. And if you have any questions right now, we can discuss as well. I think we have a few minutes left, maybe.
Thanks, Saurabh. So, I mean, you're absolutely right. This is like a quite, hot topics. That's why I just thought, although you might not be expert, but at least giving you, some idea, what is happening now, what are still, I mean, some challenges are there. So there should be like, more research and more investigation are needed to solve those issues. So any final question or comments?
So this is Chellammal. Sharat Nizami sir, can I see the previous slide, sir? Future scope. Future scope, sir. Sir, actually, there was scope for frequency regulations and reactive power support, sir. Is it between peers you mean, sir, or between the load and the grid, sir?
Not between peers. So if there is any local market, and if in a nested framework, if we can aggregate that into system level as well. So obviously the flexibility from these consumers can be used to support reactive power and frequency regulation to the market operators. So if needed, this reactive power can be traded by the network operators for any voltage issues, or if needed by the market. So for example, this consumer is, in addition to bidding in the wholesale electricity market, they can also bid in the wholesale FKS market. You can see control ancillary service market as well. So if there's any additional resources available, they can bid in the market, and this sort of nested market framework, transactive market framework, can be used to facilitate this sort of trading.
Thank
So
you,
you know
sir.
that, I mean, most of the like distributed energy resources we use, we have like a smart inverter, and that has got capability, to providing almost all of the service for the networks. Although, I mean, currently, I mean, in most of the cases, they are not participating, but, if there is a need, I think, I mean, the infrastructure is already there. So if you have got the market infrastructure, even, I mean, they could participate, I mean, in providing those like, ancillary service to the grid.
Okay, thank you, sir.
Any other question or comments? Okay, if not, I think I have still got another topics on microgrid. So probably, we just have got like, 10 minutes remaining. So I'm not starting that topics today. I'll start it tomorrow. Probably that might take like one day or slightly more than one day. And then finally on Friday, I'll solve, I mean, some problem with all of you. Okay, then probably in that case, I mean, we'll leave it here. Thanks everyone for your attention. And as Saurabh mentioned, like, even later, if you have got any question or comments, I mean, feel free to reach both of us. Thank you.
Yeah, thank you, Saurabh. Thank you so much. And thank you, Dr. Jangir. We'll be continuing this session with a lecture from Dr. Farhad on wind conversion at 3 p.m. We'll take a break of 10 minutes and then we'll again join.
Okay then. Thank you, Altaf. Thanks, Saurabh.